Welcome to the session on integration using trigonometric identities. The objectives for this session are to use trigonometric identities in integration. Sometimes we could use trigonometric identities to integrate expressions. We can therefore replace expressions which cannot be integrated with expressions which can be integrated. Let's remind ourselves of some important trigonometric identities first. Here are the angle addition formulae and the double angle formulae. Some important trigonometric identities. We can also rewrite a sine theta plus b cos theta as r sine theta plus or minus alpha or r cos theta plus or minus alpha, as shown here. And we also have some standard integrals, as shown on your screen. Here are all the formulae again, which you may be required to use. Let's now take a look at an example. We're going to use some of the formulae we saw on the previous slide to help us integrate these expressions. However, it is not always obvious how to tackle such problems, so it is a good idea to have the formulas in front of you to begin with and then simply practice. So here are the formulae. Pause the video and have a go at the example. Press play when you're ready to view the solutions. Let's take a look at part A first. We're required to integrate cot squared x. So let's solve this. However, let's think about it first. Notice that cot squared x doesn't appear in the list of standard integrals on the right-hand side of the screen. So what can we convert cot x squared to? Take a look at these integrals again and the trigonometric identities. What can we convert cot squared to, which is integratable, so to speak? Take a look at these two formulae and think about this for a moment. So let's try using this identity first. Cot squared x plus 1 is identical to cos x squared x. We can rewrite the integral now of integral cot squared x dx as integral of cos x squared x minus 1 dx. This is equal to the integral of cos x squared x dx minus the integral of 1 dx. Now we can integrate cos x squared x. As shown from the standard integrals, we can integrate this to minus cot x. And of course, the integral of 1 dx is simply x, as shown. And finally, we add on the constant of integration to give us this expression here. And now for part B. We are required to integrate sine 2x cos 2x. Let's solve this. Now, sine 2x cos 2x can be converted. Every time you see sine of an angle times cos of the same angle, you may be thinking, or you may need to think, about one of the double angle formulae. In particular, sine 2a is identical to 2 sine a cos a. And here, of course, we've converted sine 4x to 2 sine 2x times cos 2x. We've let a equal 2x. And so we can convert the integral of sine 2x cos 2x dx to integral half sine 4x dx, as shown here. Now, to integrate this expression, we're going to let u equal 4x. And this is going to help us to integrate sine 4x. And of course, u equal to 4x implies that du dx equals 4. So let's now integrate a half sine 4x. We can take the half outside the integral sign as shown. Sine 4x now becomes sine u, and dx is replaced by du over 4 as shown here, to give us this expression. We can take the constants out as shown, so half times a quarter is all now outside the integral to give us 1/8. And so we simply have to integrate sine u with respect to u. And integrating sine u gives us minus cos u as shown here. And of course we can replace the u with 4x as shown, to give us that our integral is equal to minus 1/8 cos 4x plus c. Now let's take a look at part C. We are required to integrate cot x minus cosec x all squared. So let's solve this. We begin by multiplying out the brackets as shown. Next, remember that we're going to replace cot squared x by another expression which is integratable. In particular, we're going to replace cot squared x by cosec squared x minus 1, using the identity highlighted. And we're going to leave the rest of the expression as it is. And then tidy up. So we have 2 cosec squared x minus 1 minus 2 cot x cosec x. And now we can integrate. The reason we're not exchanging any other of the expressions is that we can integrate these expressions from the standard list of integrals. So now let's take this term by term. We're going to rewrite this expression as 2 times the integral of cosec squared x dx minus integral 1 dx minus 2 integral cot x cosec x dx. And now let's integrate. So the integral of cosec squared x dx is minus cot x. The integral of 1 dx is simply x. The minus 2 is left as it is here. And the integral of cosec x cot x dx is equal to minus cosec x. And of course we need to add on the constant of integration at the end, as shown here. And so tidying up, we have minus 2 cot x minus x plus 2 cosec x plus c. And so we have our integral. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We're required to find the exact value of the integral shown on your screen. Now notice in the denominator we have again this expression sin x cos x. Of course we have sin squared x cos squared x, but if you think about it in another context, it's actually sin x cos x all squared. And we're thinking about this in these terms so that again we can use our double angle formula for sine. So we rewrite our integral as shown here, with sine squared x cos squared x replaced by sin x cos x all squared. And now we can replace sin x cos x by a half sin 2x using the double angle formula shown. If we square a half sin 2x, we obtain a quarter sin squared 2x. 1 divided by a quarter is simply 4, and we take that outside the integral as shown here. And inside the integral, we're left with cos x squared 2x. And hopefully you'll be able to recognise that cos x squared does appear in our list of standard integrals. However, it doesn't appear in the form cos x squared 2x. So let's let t equal 2x and then try integrating. We're going to replace 2x by t. And of course, this will mean that we need to replace dx with something as well. Now, t equals 2x implies that dt dx equals 2. So let's refine our integral. We're going to change the limits for x values to limits of t values. And of course, since t equals 2 times x, the limits are going to be multiplied by 2 as well. So pi by 3 goes to 2 pi by 3. And pi by 6 goes to 2 pi by 6. Cos x squared 2x is now cos x squared t. And dx is replaced by tt, and the fraction is divided by 2, as shown. Now let's work with this integral. The limits have to be tidied up. 2 pi by 3 remains as it is, but 2 pi by 6 becomes pi by 3. 4 divided by 2 is 2, and this 2 is taken outside the integral sign as shown. And now let's integrate this expression. The integral of cos x squared t dt is simply minus cot t, as you can see from the standard integral in the list. 2 pi by 3 is one of the limits at the top, and the lower limit is pi by 3 as shown. So let's now calculate this expression. We have 2 times minus cot 2 pi by 3 as shown, minus cot pi by 3 as shown here, to give us 2 times minus root 3 over 3 plus root 3 over 3. And this is equal to 4 root 3 over 3. So we've found the exact value of our integral. This brings us to the end of this session. If you have understood its contents, you should be able to use trigonometric identities in integration. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.